In this lesson, we're looking at trapezoids and kites, special quadrilaterals, four-sided shapes. So the first thing we're going to be able to do is find areas of those kites and trapezoids. We use area quite a bit. The most common place, the place that I've used it the most, is whenever I've had to paint any rooms in my house. They tell you how many square feet it will cover, so that tells you how much area it'll cover. So you got to get an idea of how big your walls are. So if you have any odd-shaped walls, you'd be able to use these formulas. If you have vaulted ceilings, you get like trapezoid-shaped walls. So that's the way it works out. And then obviously when you can apply the properties and correctly calculate area, you know you've got it. So first of all, a quadrilateral is a polygon with four sides, four-sided figure. So quadrilaterals have four sides. That's what quad means. So we can name all of the sides. There are four sides. It's got side QU. It's got side UA. It's got side AD. And DQ or QD, whatever way you want to say it. It also has four angles. Each of those is an angle. Angle Q, angle U, angle A, angle D. One thing we're going to be doing quite a bit with in this unit, all about quadrilaterals, is talking about diagonals. When you go across from one corner through the middle to another corner, that's a diagonal. And you can go the other way too, from Q to A. So quadrilaterals have two diagonals. UD is a diagonal, and QA is a diagonal. They go through the middle. The angles, we talked about triangles, how the angles add up to be 180. For quadrilateral, the angles add up to be 360. The easiest explanation for why that works without going through a whole proof, if I delete this line right here, when you draw a diagonal, it creates two triangles. Here's a triangle, and then down here. So the angles inside this triangle add to be 180. The angles inside this triangle add to be 180. There's two triangles, so that means total would be 360. So now we're going to look specifically at a kite. A kite is a quadrilateral with two distinct pairs of congruent consecutive sides. The definition is a little bit confusing, but once you tie it to a picture, it's going to make sense. So there's two different side lengths. Those two sides that are consecutive, they're next to each other, are congruent. And then same thing over here. These two sides, which are consecutive, are also congruent. And it does look like a kite, like what you would play with on a windy day. I draw the tail string. So you got to have the sides next to each other congruent. Really what that does, and we'll be using this very soon, I like to think of it, if you split it down the middle like that, you draw in the diagonal AC, you get two triangles. Not just any two triangles, you get two different isosceles triangles because these two sides are congruent and those two sides are congruent. So you get two different isosceles. If you can think of it that way, that actually really kind of leads you to all the properties about kites because there are isosceles triangles inside them. So here's those theorems we were talking about. So one thing that's going to happen is you draw in both diagonals. They are perpendicular to each other. They're perpendicular to each other. That makes a right angle. The second theorem that we're going to talk about exactly one pair of opposite angles are congruent. Kind of comes from that isosceles triangle thing I was talking about. These two angles, A and C right here, those two angles will be congruent. Just like in isosceles triangles, you get the base angles are congruent. If we drew this as isosceles triangles, those angles at A and C become the base angles. The other thing that happens is one of the diagonals bisects the pair of non-congruent angles. So this diagonal, BD, it bisects both angle B and angle D. Angle B gets cut in half, and angle D is bisected also. It's cut in half. So we can name those angles angle ABD over here in blue will be congruent to angle CBD. And same thing on the right side over here at angle DADB. Is congruent to CDB. Because the angles are bisected. They're cut in half over there. Might as well write the diagonals are perpendicular as a expression also. BD is perpendicular to AC. And then the last property, one diagonal bisects the other. So these lines that are now drawn in here, BD into AC, one of them gets cut in half. You can tell pretty easily by looking at it to see which one gets cut in half. BD, that's not equal sides. So it's these on AC right there. One diagonal bisects the other. BD bisects AC. Now on to trapezoids. Trapezoids have one pair of parallel sides. Normally it's like the top and the bottom. So there's a little bit of just some careful wording here. It says exactly one pair of parallel sides. That means it can only have one pair. Cannot have a second pair of parallel sides or a second pair of parallel sides. When it says at least one, that means it could have one or more. So I've actually seen it written both ways a little bit, but if there's more than one pair of parallel sides, then we're going to call that parallelogram, but that's for future. So I use trapezoids for exactly the one pair of parallel sides. That's the definition I use. So one pair of parallel sides. Normally, like I said, it's the top and the bottom. DE is parallel to GF. That makes a parallelogram. Trapezoid. There's a special trapezoid, isosceles trapezoid, just like an isosceles triangle, where the two sides, the two legs are congruent. That's what an isosceles trapezoid is. The legs are congruent. And that would be the non-parallel sides. So isosceles trapezoid would look like this. You've got the top and the bottom, parallel sides, and then the left leg and the right leg, those are congruent. So isosceles trapezoids have some special properties. So by definition, we've got to have parallel top and bottom. The two legs are congruent. What that means, just like isosceles triangles, the base angles are going to be congruent. The base angles will be congruent. That doesn't just mean K and J, though. It actually means H and I also. 2 at the bottom and the 2 at the top. K is congruent to J. Angle H is congruent to angle I. And the other thing that this says right here is that opposite angles are supplementary. So that means angle H and angle J are opposite. Add the 180. And same thing with K and I. Angle K plus angle I, they add to 180. Because they are supplementary. Then the other thing that happens is the diagonals are congruent. So diagonal KI is congruent to diagonal HJ. So here we're going to look at an example with a kite. We use all those properties about the angles that we wrote down a little while ago. So remember, there's angles that are congruent to each other. There's quite a few. And it is a quadrilateral, so if we needed to, we could say that all the angles are going to add up to be 360. So we're told angle ADE is 24. I'm going to fill that in. And ABE is 43. So there's a lot that we know about these. For a kite, diagonals are perpendicular. So we got all these 90-degree angles in here. Diagonals are perpendicular, which means this makes 4 right triangles. So if we just look here, that's a right triangle. And triangles always add, the angles always add to 180. So this angle's 90, this one's 24. We can figure out up here by angle A, DAE, what that measure is. So 24 plus 90 is 114. And that means that this angle up here by A has to make it be 180. So 180 minus that, 66. We can do the exact same thing to figure out this other right triangle from AEB. So angle BAE. 90 and 43, this one's got to be 47. So that they all add up to be 180. Then we've got that other property that says that one of the diagonals is an angle bisector. So since this is 24, so is this side, because it's an angle bisector. Since this is 43, so is this side, because it's an angle bisector. And then you can go about this a couple of different ways, but if you draw in just this diagonal, AC, if you're just looking at this, This is an isosceles triangle. Remember from what I told you before about how these sides are congruent? That's isosceles, which means these base angles for the isosceles triangle are also congruent using the isosceles triangle theorem. Same thing on the other side. AB and BC, those sides are congruent, so these angles here are also congruent. So really what this does, and what you can kind of think of as a little bit of a shortcut, you get a bunch of different congruent triangles. Triangle ADE is congruent to triangle CDE. Those two triangles are congruent to each other. You can do a lot of different reasons here. Here's, for one, angle side angle. A lot of different ways you can go about it. You can do the same thing with these two triangles, the blue stars, ABE and CBE. Those are congruent triangles also. You could even just looking at one diagonal, just this one down the middle, it makes larger congruent triangles. This one you would know because, well, you can say side, 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 using DB as the reflexive side. Tons of different ways. But kites make a lot of congruent triangles. We did find all the angles. That's really all we had to do. And if you checked and added all of these up, not the 90s in the middle, but the angles going around, angle A altogether, angle B altogether, angle C altogether, and angle D altogether would have to be 360. All right, here's a trapezoid. We're going to do basically the same thing. Since it's a trapezoid, you know you got those two parallel sides. So one thing about trapezoids, we didn't explicitly say, but since these sides are parallel, this is kind of like a transversal. So you've got two parallel lines with a transversal, which means you get all those angles. Alternate interiors are congruent, alternate exteriors are congruent, corresponding is congruent, and same side interior are supplementary. So if we're looking at angle Y and angle 68 degrees right here, those are same side interior, which means they are supplementary. So that means angle Y plus this angle, 68 degrees, equals 180, because they're same side interior. You could do the exact same thing over here to get angle X plus 113 equals 180. And you can solve for X and Y. Angle Y is 112. And X, 67 degrees. So if this is an isosceles trapezoid, AC, they're telling us this diagonal, and BD, that's the other diagonal. One of the properties we said about isosceles trapezoids is that diagonals are congruent or equal. So these are the diagonals. They have to be congruent, which means they have to be equal. So what's the value of x? Solve for x. We get 4x equals 12. So x is 3. If you plug that in, you'd get the same answer for both of those because they're equal. Area of a kite. There's a couple different ways to do it. One of them would be, we talked about how this makes 4 right triangles. You can find the area of each triangle. But a much, much simpler way is diagonal times diagonal divided by 2. So for a kite, diagonal times diagonal divided by 2, which is actually similar to the triangle formulas, like 1/2 base times height, kind of what it works out to be. So find the area of a kite with these coordinates. So we're going to plot it. We're going to see how long each diagonal is and find the area. Here's A and B, C, and D. So we've got our kite. We can find our diagonals. This is an easy one because you can count how long the lengths of the diagonals are. So BD, you can count that out. That's 6, 7, 8, 9, 10. And then AC, the other diagonal. Count that one out. 11. So there's our 2 diagonals. We said that the area for a kite is diagonal times diagonal divided by 2. $110 divided by 2 is 55. Put some units on there. It didn't give us what the units are, so that's just the word units squared. Area is always squared. I'll write that better. 55. For the perimeter, it's the same shape. You have to find all those side lengths. To do that, you know that they're going to be, some of them are going to be the same. Those 2 are the same, and those 2 are the same. To make those side lengths, you have to do Pythagorean theorem. A squared plus B squared equals C squared. So if we take each of these little triangles here, this side is 2, 1, 2, 3, 4. This side is 5. So we can find AB, which is the same as AD, using Pythagorean theorem. We get that it is the square root of 2 squared plus 5 squared. Using distance formula would be the exact same result. So that's 25 plus 4 is 29. You can get the other two sides doing the same thing. This side it's 5. 1, 2, 3, 4. This side is 9. So we can do BC, which is the same as DC. Would be 5 squared plus 9 squared equals hypotenuse squared. So that's 81 and 25. It's 106. We can add up all of those sides for perimeter. It's square root of 106 plus the square root of 106 plus the square root of 29 plus the square root of 29. Means you get square root of 106 twice. And you get the square root of 29 twice. And you can put that into your calculator. And you get that it's about 30.789 units. For a trapezoid, we got this formula: 1/2 the height plus or times the sum of the two bases, base 1 plus base 2. So if we plot these points, we get this trapezoid here. So we can see our two bases, AB and DC, are parallel. They're both flat with our parallel with the x-axis. So the area, 1/2 the height. Height we have to measure straight up and down. The height is 7. And then base 1 and base 2. This side is 12, and then this side is 6. So that's 18 times 7 times 1/2. That's the same as 9 times 7, so 63 units squared for area.